The part 2 is the study of displacement and deformation. So let's start with what is displacement. You have a bar. And at some point on the bar, I take a marker, a red marker, like that, and I paint it. I paint one spot on the bar. This point here is point P on the bar. Then I apply loading. I don't even bother to describe what the loadings are. But after I apply this loading, can be forces, doesn't matter. I'm pulling this way, pushing that way. All what I'm looking now is how the shape of the bar changes. So I look at the shape after the bar deformed, and I see that the same point, point P, now is here. So it was here, and now it's here. Let's say that I make my x coordinate axis like that. Okay? How much point P moves is called the displacement of point P. This guy here, and it goes in the x direction. So this guy here is called ux of point P. The ux is the displacement of a point in the x direction. And the reason that it has an x over here, let's do a little aside, is that ux is the x component of the displacement and in general, the displacement is a vector. It's a displacement vector. And for instance, if you are in 3D, say that I have a balloon. I have a balloon. That's my balloon sitting in a 3D space. I can do x, y, z. And now my balloon, I blow it up, and my balloon becomes something, oops, that's a very ugly balloon. My balloon that is very misshapen becomes something that looks like that. And this eye here, okay, then these are still my eyes of the balloon, the same spot that I had been drawing on the balloon. This eye of the balloon has moved here. And this is the u vector in 3D of where the eye has gone. Okay, so in general, the displacement vector has 3 components. It's going to have a component in x, it's going to have a component in y, it's going to have a component in z. Not only that, but it is a field in the sense that the displacement of this point, the displacement vector of this point, is different, say, from the displacement vector of another point. Say that my smile went over here. See, they have different displacement depending from where you start from. So in general, u is a u of x, y, and z, and is a displacement field. In general, in 3D, if you have a structure that has a shape, it deforms, it moves around in all directions, every point inside the structure is going to have a displacement, and displacement has 3 components. Now, we are working in a one-dimensional world, so all what we are interested in is the displacement in the x direction, and this is the displacement in the x direction of this point P. Now, this comes something which is really an important part of our story on axial loading that's going to help us immensely to figure out how all the equations fit together. Okay? So this is a kinematic assumption. Kinematic assumption. For axial loading. The kinematic assumption is the following. If I look at point P is going to be sitting on a section of the bar. So I look at all the points on the section of point P, and all these points are at coordinate xp. the kinematic assumption is that all points at xp move by the same ux. So the ux is a ux of xp. So if you look at these sections here, this is my section P, this point is going to move by a certain amount, and every other point moves exactly, whoa, that's a bad one. Okay, let me redraw it. Okay, so this is the section at xp. So if this point moves by a certain amount, then each point on this section moves exactly by the same amount, like that, so that they all move to the right by the same u. And because the u is the same, it's going to be ux of xp. It's the x displacement of the whole section. You see? So the consequence of that is that the cross-section stays flat and displaces by ux of x. So different points, different sections along the bar will displace by a different amount. See, this section here doesn't displace much, the one next to the wall, you see? This section here displaces by a lot. But the important thing is that every guide, every point that's on each section, they move together. They're friends. Okay? Hold hand. Woo! Let's go. Everybody goes. Okay? Brilliant. Now, this is going to help us figure out what is the deformation and axial strain. So life is much easier now, because if this is the shape that my bar had in the beginning, and let's say that this is a section that happens to be at x. So this is my x section. And then I go a little further along by a distance dx, and I look at another section here. So this section here is at x plus dx, right? So that's what the bar looks like in the beginning, when it is totally undeformed, before I apply any load to them. Okay? That's the bar. Now I go and I apply, and it's attached here to the wall. Now I go and I apply load, and my bar changes shape, becomes longer in this case. And this section here, the first section that was at x, now is someplace here. So this moved up to here. This section here now happens to be up here. So this section here now has moved up to here, so that this little segment of the bar here now looks like that. And I'm making it big, right? You have to imagine a tiny slice, but I'm making a big slice so you can see it. Okay? All right? I'm going to make a slice and that. So how much this slice moves from here to here, this is our ux of section x. How much this slice moved, this is ux of x plus dx. You see? Brilliant. So what is the, and notice that they all move, all the guys move by the same amount, so ux is only a function of the coordinate x. So what is the change in length? So actually, what is the original length of this segment? Oh, well, I told you how much it is dx. I'm not even going to bother asking you for real. The original length is dx. But now, what is the change in length? Remember what we called the change in length last time? We called it elongation, right? The change in length, elongation, for this little segment is, well, say that I have the same, say that ux is the same for this section and this section. Say that they move together by the same ux. Would that be a change in length? So why does this change in length? It changes in length because this one moves by the ux and this moves by a different amount. So the change in length is how much this guy has moved minus how much this guy moved. So the change in length is going to be u of x plus dx minus u of x. Okay, so now we're ready. What is the deformation? What is the deformation measure? Remember how we defined the deformation measure in the case in which everything was uniform, the thing that we did yesterday, right? The measure of deformation is how much I change in length divided by my original length. So if I divide my elongation by the original length, I get u of x plus dx minus u of x over dx. Who is this guy? du dx. dux, that's a very ugly u. dux dx. This thing is a measure of the deformation. What did we call the change in length per unit length last time? Any name? Did we call it stress? Did we call it stiffness? Did we call it Joe? What did we call it? Strain. Strain, axial strain. And now, is this axial strain the same necessarily over the entire bar? Now this is going to be the axial strain that happens at section x. And it may change from point to point. And it's the same for every point at the same section x. Okay, so now we have epsilon axial of x. Excellent work, guys. You've been working so hard. Okay, so what do we do with epsilon axial of x? Before, yesterday, we know that if we want the elongation of the bar, and this is uniform, I just multiply by each other, and boom, I get the elongation. Now, if my strain changes from point to point, it cannot be as simple as that. So what is my strain to elongation story? If I had a little chunk of length dx, and then this displaced, now it is longer, the change in length is du, right? The change in length between the original length dx and the final length is du. So if I have the bar, each little guy, so the change in length for each little segment is du, right? dux, which I can also write as dux dx multiplied by dx. This is how much each little dx changes. So if I want the whole change in length, I need to sum it up from the beginning to the end of the bar. This is going to be our elongation of the bar. Instead of writing dux dx, I can write is equal to the integral from 0 to L of epsilon axial of x in dx. Now you see that this is the generalization of what we did last time when we said the change in length is simply strain multiplied by the original length because strain was uniform. If strain is uniform, I can take it out and I get back that the elongation is axial strain times length. Okay? I've been a little sloppy here using L instead of L0. To be precise, I should be integrating over the original length. Now, I'll let you into a very convenient thing. In 201, We are only going to do small strains and small deformations, which means that in general, the change in length in the structure is going to be small compared to the original length. So sometimes we just use L instead of L0. We are a little sloppy about things because really the strains are small, the elongations are small, and even if when I draw these things, I draw them as if like they stretch like crazy. All the problems that we do, we should do them in small strain and small deformations. Okay, so this is our relationship now between the axial strain, which is constant at every x, and the elongation of the bar. Now we introduce this u of x. If I give you the axial strain, can you give me u of x? Well, I think you can, because the relationship is simply that one is the derivative of the other one, right? So if I have from epsilon a of x, can I get u of x? I can, but I also need some more help. I need boundary conditions. Because the strain is the same as dux dx. So if I have epsilon a of x, this is the same as saying that I have dux dx. So I know I can integrate dux dx in dx to get u of x, right? But I need to know how to do the constant of integration. The way you should think of the constant of integration in 201 is in a very physical way. The idea is that you're integrating dux dx along the length of the bar. And what I want you to think of is that when you write u of x, you write that the displacement at every point where you want it is equal to the displacement at some point where you know it. So where are the points where you know the displacement? How much is the displacement here at the wall? 0. The wall is where you know what things happen, what's going on. You know that the displacement at the wall is 0. So you can say that the displacement at every point in the bar is equal to the displacement at some point where you know things, typically the wall where it's 0, plus you integrate the derivative from where you know things to where you want them. Because you're integrating, this must be your variable dx prime. Okay? So it is the same as saying I integrate, and then I impose the boundary condition, and I find the constant. It's the same thing, but it's physical, right? I want you to think of it this way. You integrate the u dx from where you know to where you want it, starting from the point where you know things. So let's do a little example of how this works out, right? So say that I have a bar like that, and the bar is, the x, I do it like this. So this is x equals 0 at the wall. Say that my bar is of length L. And say that I have a strain in the bar. I come to you and I give you the strain, epsilon axial of x. I'm going to simply do a linearly increasing strain. Okay, so your axial strain is 0.1 plus a term that increases linearly with x. So let's say plus 0.2x. And because I cannot do this, because x has dimensions and epsilon a does not have dimension, I'm going to do plus 0.2x over L. So that means that my epsilon a starts at 0.1, and then when x is equal to L, I'm going to be at 0.3. Okay, so I come to you and I tell you epsilon a of x is that. You know it. Okay? And then I want you to give me what is u of x. And I tell you that the wall is at x equals 0. So you just plug that in. You say u of x is equal u at x0, and x0 is the wall, so is equal to 0 plus the integral from 0 to x of 0.1 plus 0.2 x over L in dx. As simple as that. So you integrate that, and you get the u of x is equal to 0.1 plus 0.2 over L that multiplies x prime squared over 2 integrated from 0 to x. And oh my gosh, I cannot even start telling you how important that you keep this thing in. If I had given you, well, let's finish this up and then I'll tell you. So this is equal to 0.1 that multiplies 1 plus x squared over L. 0.1x. I forgot an x here. 0.1x, 0.1x plus x squared over L. By the way, you see what happened here? I just did things without thinking much, and I forgot the x when I integrated 0.1 in the x. Whoop. That should be x minus 0, by the way. I got over here, and I was looking at my solution, and you see here that I looked at the units, and the units are wrong, because u of x is a displacement, is a units of length. Right? So I cannot have something unitless in the displacement. So that's how you find your displacement field u of x. You get the epsilon a of x, you integrate, you respect your boundary conditions. If the wall was on this side, so if instead of having the wall here, if I take the wall here, and I still keep the x like that, but now the boundary condition is like that, so that the wall is on that side, and I still have the same epsilon a of x. I didn't change that. All what would change here is that I would integrate from L to x. So instead of having x here, I would have L minus x. Instead of having x here, I would have L minus x squared when I integrate. Okay? You got to do it yourself to actually get practice, and as you do it, you will kind of remember these things, and it's going to work out. So to help you, because I totally care for you, it's going to be in a homework that you have to do something like this. And there are example problems on Stellar that we're going to post. But guess what? We're done with this part of the story. Let me see if we can finish up the story today or not. Of course we can finish up the story today. OK, so part 2. Part 3 is when we're going to make the lasagna, OK? Ready?